There are four basic phenomena that underlie the entire theory of and practice of electricity and magnetism. One, if I take two pieces of tape, put them together front to back, tape's not cooperating, and strip them apart, they will attract each other. If I take two more pieces, do the same thing. One of those pieces will attract, say, this piece, and the other will repel it. From this, we conclude that there are two types of charge, and that the strength of attraction or repulsion, well, if we do further measurements, strength of attraction or repulsion is inversely proportional to the square of the distance between charges, and we get Coulomb's law. Okay, if we take a coil of wire and attach one end of the coil to one terminal of a microammeter, the other end to another terminal, and I'm not going to actually demonstrate this, but we've done this in lab, and move the coil back and forth, and or rotate the coil in front of the magnet. Okay, rotate it back and forth. We change the magnetic flux through the coil, and that results in a current. And we conclude from that that the changing magnetic flux creates a potential difference, creates an electric field. We'll talk about the details shortly. If we have a current in a wire, and let's say I have a wire down here, so we run a current through this wire, and we hold a compass above the wire. Then the compass is going to deflect depending on the current, and it's going to deflect in a direction that's perpendicular to the current. If I hold the magnet under the wire, the magnet will deflect again in a direction perpendicular to the current, but in the opposite direction, under as opposed to over. And then we expand these measurements. We find that there is a magnetic field that surrounds the wire, and if it's a long straight wire, the magnetic field follows circular field lines, circular field lines around the wire that fall off with our distance from the wire, and we can modify and expand those experiments to develop a theory of what's going on. That's going to give rise to the third idea, that we have for any length delta L with a current I, we can take a vector r from that segment out to the point at which we want to calculate the field, and we get something that's very much like an inverse square law. We'll talk about the details of this law, but this follows from a refinement of the phenomenon we see with the compass above the current in the wire. And then we can take an aluminum strip. It doesn't have to be aluminum, but aluminum is convenient because it does not react magnetically, and run that over the top of a magnet, then run a current through the strip, and the strip is going to deflect. It turns out that the deflection is in the direction perpendicular to the magnetic field as well as perpendicular to the current. And from that we get our fourth observation.